Hello, welcome back to Honors Topics in Physics. So we know so far that a net force, an unbalanced force, will cause an object to accelerate, but there's more to it than that. Let's say I were to apply the same force somehow to a purple bowling ball and a tennis ball by, let's say, blowing them with a leaf blower. Are they both going to accelerate the same? No, I don't think so. That tennis ball is going to take off, and then that bowling ball will be trailing behind it because it's going to accelerate at a slower rate. Okay, so even if I were to apply the same force to two different objects, they're going to speed up differently depending on their mass. Okay, we can express this as Newton's first law or Newton's second law, F equals ma, where it says the force required to accelerate a mass m at acceleration a. Okay, so F, the force, whatever force is required, is based on the mass times the acceleration. And it says an object is going to accelerate in the same direction as the net force is applied. So an object will accelerate in the direction of the net force proportional to its mass. Okay. So units on this, so if I multiply and mass times acceleration, that's kilograms times meters per second squared, I end up with a kilogram meter per second squared, which, as we know from before, is abbreviated as a Newton. Okay, a Newton is not a ton of force, it's about the weight of an apple. So 1 Newton of force isn't going to knock you over, but you'd be able to feel it. If I rearrange F equals ma in solving for acceleration, so A equals F over m, what we can see is, okay, if I increase the force, what's going to happen? If I increase the force number, what's going to happen to this side of the equation? It's going to get bigger or smaller? It's going to get bigger. Okay, and since this side gets bigger, so does this side. Okay, and basically mathematically that's just saying that if you apply a greater force, if you increase the force, the acceleration is greater. And what about if we increase the mass? Let's say I make this number bigger. Does this side still get bigger? No, because I'm dividing by that number. So if I divide by a bigger number, this side will get smaller, and thusly, because of the equation, the equal sign, this side will get smaller. And what that means is the more mass you have, the bigger the mass, the smaller the acceleration. Okay, so things that we already kind of know, just expressed mathematically. Let's work a few problems here. Let's say we apply a 800 Newton force and to a 1200 kilogram car. What's the acceleration? So we're given the force. Okay, we're given what are we given here in kilograms? We are given the mass, and we're looking for the acceleration. So plugging that into the equation, 800 equals 1200a, so 800 divided by 1200. So we get an acceleration, a would equal 0.67 meters per second squared. Okay, what force is needed to accelerate a 1300 kilogram car at 2.5 meters per second squared? So this time we're looking for force, okay, and that's going to equal the mass times the acceleration. Okay, so 1300 times 2.5 gives us 3,250 newtons would be our answer to that question. Okay, an object has a 3 kilogram object has 200 newtons of force pushing it forward and 650 newtons pushing it backwards. What is its acceleration? Okay, so we're back to looking for acceleration, but we're given two forces. What should we do with these two forces? Should we work two separate problems? Should we add them? Should we subtract them? Well, one is pushing the object forward and the other one's pushing it backwards, so those are going to partially cancel. And we're going to end up with 450 because we're going to subtract them. Wait a second. We should end up with 650. We should end up with 400, shouldn't we? There we go, having corrected that minor clerical error. So minus 400. Now, why is the negative there? We subtracted the numbers because they were in opposite directions, so that makes sense that they'd be 400. But why the negative? It's because the bigger one, the 650, was pushing it backwards, so that's why it's negative. So take that and divide by 3. F equals m, or m is 3. we get negative 133 meters per second squared. What about if we have a 3 kilogram object, if we got 250 pushing it forward and 250 pushing it backward, what will its acceleration be then? Okay, well, I've got 250 forward, that's plus 250 as far as the force goes, and I've got 250 to the left, that's negative 250, so that's going to be 0. My net force is going to be 0 because the forces are equal and opposite, so my acceleration is 0. Lastly, what force would be required to accelerate a 40 kilogram asteroid from rest to 20 meters per second in 5 seconds? Well, if I'm going to solve this, F equals ma, I'm going to be using F equals ma. This is really the other than F of g equals mg, F equals ma is our equation for this unit. So we're using that one. We're trying to figure out the force, which means we need the mass, which we're given as 40, and the acceleration, which we need. But we're not given the acceleration. We're given an initial velocity, a final velocity, and a time. Going back to the previous unit, remember that the acceleration is equal to v2 minus v1 all over t. So we're going to solve for, I don't know why that's a capital A, but v2 is 20 minus v1, which is 0, divided by the t, which is 5. So my acceleration is going to equal 4 meters per second squared. Okay, and then plugging that into F equals ma. Okay, where our m is 40 kilograms and our a is 4. They're just juxtaposed, but it doesn't make a difference. 40 times 4 is 4 times 40. And we're going to end up with 160 newtons of force would be required to accelerate that object. Okay, going back to something that we've already learned, and I want to kind of recap why it is true. If we were to drop a 1 kilogram and a 10 kilogram mass, which would hit the ground first? Well, they both hit the ground at the same time. Okay, why would that be? Okay, well, we learned from before that force of gravity equals mass times gravity. So the more mass an object has, the more weight it has. Okay, and weight's a force. So therefore, this thing has got 10 times the mass. Therefore, it's going to have 10 times the force accelerating it, won't it? Well, that should give it 10 times the acceleration, shouldn't it? If I have 10 times the force accelerating it. Okay. Well, it would, except that this object also has 10 times the inertia, or 10 times the mass. So it ends up that that perfectly balances out. Okay, if it has 10 times the weight, it's going to have 10 times the inertia. It's going to accelerate at 9.8 meters per second squared. If it had 5 times the mass, it would have 5 times the weight, and it still would have accelerated at 9.8 meters per second squared. So that's why all things fall at the same rate. Newton's second law. Let's say I applied the same force to a 1 kilogram and a 2 kilogram object. Let's say I applied the same force. Compare their accelerations. Okay. Well, the 1 kilogram is going to accelerate twice as fast. Okay. And those are some multiple choice questions, examples like I like to ask. The 1 kilogram is going to accelerate at twice the rate. Okay. After 1 second, the 1 kilogram mass will have gone how many times as far? Okay, the same distance, twice as far, half as far, 4 times as far. Well, it's going to, if it accelerates, delta y equals at squared over 2, and be, well, according to our equation, delta y equals at squared over 2. If I double the acceleration, if I double the a, I'm going to double this whole quantity. Okay, so that means that the 1 kilogram object will have traveled twice as far, not 4 times as far, because we're not doubling the time, we're doubling the acceleration. Let's look at some mathematically fairly simple examples, but conceptually make you think. So let's figure out the acceleration of these objects in this slide here. So we've got 100 kilograms, 100 newtons pushing it forward, and 100 newtons pushing it back. What's its acceleration? Well, the net force is going to be 0, so F equals ma. So my force is 0, so my acceleration is going to be 0. That's my first one. What about this one? Are those forces going to still subtract, or are they going to add, or am I going to use Pythagorean's theorem? Well, they're both going to the right. So 100 to the right and 100 to the right gives me 200 to the right. So if my force is 200 and my mass is 100, my acceleration is going to equal F over m is going to equal 2 meters per second to the right, or 2 meters per second squared, sorry. Okay, let's look at this one. Let's see, my net force is going to be 100 newtons to the left, or negative 100 newtons. My mass is 100, so my acceleration should be negative 1 meter per second squared, okay, or 1 meter per second squared to the left. Here, am I going to add these two like I did here and get 200? No. Since they're at right angles, remember we use Pythagorean's theorem, and if I add these two, I'm going to get, using Pythagorean's theorem, I'm going to get 140, and my acceleration would be 1.4 down and to the right. Okay, so key thing here is that when we're dealing with the acceleration, it's the net force that determines the acceleration. We've got to look at both of our forces, or all of our forces, in order to figure out what the net force is, and that's going to be the acceleration, or is going to determine the acceleration. Okay, let's look at a few more examples here, and then we'll be done for the day here. Let's see. We've got a rope that pulls up on a 5 kilogram bucket with a force of 120 newtons. So I'll draw my little free body diagram here. So I've got 120 newtons up, okay, and what's the bucket's acceleration? So remember what we just learned is that it's the net force that determines the acceleration. Okay, now this 120 newtons of force acting up on it is not the only force acting on it. It says don't forget about gravity. So gravity, remember, F sub g is equal to m times g, mass times gravity. So 5 kilograms times 9.8 gives me 49 newtons. Okay, and we're trying to figure out the acceleration, so we need to figure out the net force. Now we've got 120 up and 49 down. Okay, so these are going to subtract because they're in opposite directions. So the 120 is going to be positive. So 120, we're going to add to that a negative 49, or subtract 49 from it, and we're going to get 71 newtons. Once we know the net force, we use F equals ma. And 71 is my net force, equals my mass, which is 5, times my acceleration, which is what I'm looking for, and we get 14.2 meters per second squared. So we had to calculate the force of gravity, calculate the net force, and then use F equals ma. So a couple steps there. How much force would the rope have to apply to move the same 5 kilogram bucket upward at a constant 2.5 meters per second? Okay, so we want to figure out, in this case, we want to figure out what the net force is. So we need to know what my acceleration is. Well, it says we're moving upwards at a constant to 2.5 meters per second. That tells me that my forces are balanced. Okay, so that's the tip-off that all of my forces cancel out. Well, I still have that same 49 newtons down, okay, and that's got to be canceled out by the force of tension in order to balance my forces. So my force of tension in this case is just equal to 49 newtons. Okay, because we're moving upwards at a constant 2.5 meters per second. If we were accelerating upwards at 2.5 meters per second squared, it would be a different problem altogether. As a matter of fact, it'd be this problem. Okay, what is the tension required to accelerate a 5 kilogram bucket upward at 2.5 meters per second squared? Okay, so what we want to do is we're trying to figure out this force, this force of tension. We know gravity is still 49 newtons down. Okay, let's figure out what the net force is. What net force would be required to do this? So the net force is going to equal the mass times the acceleration. 5 times 25 equals 12.5. That means I must have a net force of 12.5 newtons up, okay, in order for this, in order to accelerate at that rate. Well, I've got 49 down, okay, so it's going to cancel out with 49 of those newtons, and I need 12.5 left over. So if I add those two together, 49 plus 12.5, I get 61.5 newtons. And then if I were to put that here and say this was 61.5, and I were to add those two, I would end up with 12.5 newtons left over. So that would be that example. Don't need to worry about that. All right, and so you've got a force equals mass times acceleration worksheet. Work on that. Make sure you show your work for problems, and good luck.